Hi everyone, and welcome back to the Trending Tech Show. I'm your host Alex, and today we're taking a deep dive into an area that affects every single application you use, but that most people hardly ever think about: how databases actually store and retrieve your data. With me today is Mike, a database expert who's going to help us break down the world of storage engines, indexing, and what happens under the hood every time you click save or search for something. Mike, thanks for joining us.
Thanks for having me, Alex. I'm excited to be here. Storage and retrieval are such foundational topics. It's amazing how the right storage engine choice can make all the difference in performance, scalability, and reliability.
Absolutely. I think a lot of developers, especially when they're just starting out, see a database as this magic box. You put data in, you ask for it back, and it just works. But obviously, there's a lot going on behind the scenes. Could you set the stage for us? On the most basic level, what do we mean when we talk about storage and retrieval in databases?
Sure thing. At its core, a database's job is actually pretty simple. When an application gives it some data, say new user info, a product update, or a log entry, the database needs to save that data somewhere persistent and then, later on, be able to efficiently retrieve it when asked. So, storage is all about how we write the data and keep it safe, often on disk. And retrieval is about how we quickly find and return that data again. Easy to say, but when your database grows from dozens to billions of records, that simple goal becomes a major technical challenge.
That makes sense. And I know that as applications grow, choosing the right way to store and retrieve data isn't just a technical detail anymore. It really affects how well things work. So let's dig into some specifics. How do databases actually organize the raw data and make sure it can be found later?
Great question. Databases use a variety of what we call storage engines and indexing structures to manage data. There's two main families you'll hear about: log-structured engines and page-oriented ones, like B-Trees. Each family has its strengths, and which you use depends on your application's needs. Let's start with the simplest example. Imagine a key-value store that just appends every new piece of data to the end of a file. Think of it like writing every new thing you want to remember at the bottom of a long list. If you want to find the latest value for a key, you have to read from the top all the way down, looking for its last appearance. This approach is basically what some systems, like Bitcask, use. Appending is fast, but searching becomes slow as the file grows, unless you add an index.
Okay, so it sounds like the right part of storage is straightforward. You just keep tacking information onto the end of the file. But the hard part is finding things later. Is that where indexes come in?
Exactly. Think of an index like the index at the back of a book. It points you to exactly where to look. In that simple log I described, if you kept a separate hash map in memory, mapping every key to the position in the file where its value lives, you could jump directly to the right place instead of having to read the entire file. This is why in-memory hash tables are popular in systems where you can fit all your keys in RAM. They make lookups lightning fast.
Just to clarify for our listeners, a hash table is a data structure that lets you look things up very quickly, almost instantly, if you know the key, right?
That's right. Imagine a super organized librarian who knows exactly which shelf and row holds any given book. Hash tables do the same. They turn a messy pile of data into a lookup system where you hand over a key and instantly get the address of the value. The catch is that all those addresses, the hash map, have to fit in memory. If you have more keys than your RAM can hold, you hit a wall.
So this works great if your key set is small, but it doesn't scale if you have millions or billions of different keys, right? And what about searching for a range of keys? Like everything between key A and key Z.
Hash indexes are awesome for quickly finding one specific key, but not for scanning a range. For those kinds of queries, you need a different data structure. Before we move on, there's another problem with those simple append-only logs. If you keep updating the same key, you're going to have a lot of duplicate data in your file. To prevent the file from growing endlessly, databases periodically perform compaction. They break the log into segments, merge them by keeping only the most recent value for each key, and throw away outdated or deleted entries. This keeps things tidy and makes lookups faster.
So compaction is kind of like cleaning up your closet, getting rid of duplicates and old stuff. But we still haven't solved the range query issue, right? Is this where sorted string tables and LSM trees come in?
Exactly. SS tables, or sorted string tables are another step forward. Imagine instead of writing data in whatever order it comes in, you keep everything sorted by key. If you do that, you can quickly scan a specific part of the data. For example, all keys starting with cat, because you know they're grouped together. Maintaining sorted order on disk is tricky if you're constantly getting new data. So what SS tables do is keep new or recent writes in an in-memory sorted tree, often called a memtable. When the memory fills up, you write all those sorted entries out to disk as a new segment. Over time, you merge older segments, always keeping data sorted. This process forms what's called a log-structured merge tree, or LSM tree.
So the main advantage is that range queries become efficient because the data is in order, and merging sorted files is efficient too. But how does it actually handle writing? Do you still get the fast append behavior?
Yes, that's the beauty of LSM trees. New data is always appended to a memtable and logged for safety, so you don't lose anything if there's a crash. Fewer random writes on disk, mostly sequential writes. When things get merged, it's usually large sequential blocks, which is very fast on both spinning disks and SSDs. And you're right, because files are sorted, you can use sparse in-memory indexes or tricks like Bloom filters. A Bloom filter is a clever way to quickly check whether a key might exist in a file without reading the whole file, like a bouncer at a club who can immediately tell you, "Sorry, your name's definitely not on the list," saving you a trip inside.
So, just to recap, structured storage engines, Bitcask, LevelDB, RocksDB, Cassandra, HBase, all use logs, compaction, and sorted or unsorted segments to optimize for high write throughput. But there's still another big player in the index world, B-trees. How do those compare?
Absolutely. B-trees are the classic database data structure, especially in traditional relational databases. Instead of storing data in logs or segments, they break data into fixed-sized blocks or pages, typically around 4K in size, matching the physical disk's block size. Here's how it works. Imagine a decision tree in a phone book. The root page has keys and pointers telling you which child page covers which range of keys. You keep following pointers down until you hit a leaf page, which contains the data or a pointer to it. The key benefit is that B-trees stay balanced. The tree's depth is kept small, so even with millions of keys, you only need a few steps or disk reads to find something.
That's a great analogy. So, B-trees are a bit like a librarian who organizes all the books by alphabetical order and categorizes them in sections, shelves, and so on, making it easy to narrow down where to look, fast.
Precisely. And because the data is on fixed size pages, if you want to update or delete something, you can just find and overwrite the relevant page. This is called update in place, in contrast to LSM trees, which do not rewrite files but instead append new records and merge old ones. With B-trees, you do have to be careful with concurrency and crash recovery, so most B-tree based databases also keep a write-ahead log, a tiny append-only file recording every change before it gets applied. That way, if something bad happens mid-update, you can recover safely.
So, comparing the two, LSM trees mainly do append-only writes and merge, making them great for write-heavy workloads, and B-trees update in place, usually offering faster read performance for a broad range of queries. Is that about right?
Exactly. LSM trees are favored for workloads with lots of writes, think sensor data, logs, analytics pipelines, whereas B-trees tend to excel at read-heavy or mixed workloads where consistent low-latency reads and strong transaction support is important. Relational databases like PostgreSQL and MySQL use B-trees as their default indexing structure for this reason. But it's worth noting that the lines are blurring. Newer databases are mixing and matching these concepts to get the best of both worlds.
That's a great foundation. Now, we've talked about the core indexing structures, hash indexes, log-structured approaches, SS tables, LSM trees, and B-trees. But real-world queries often need to look up data in more than one way, right? That's where secondary indexes and more advanced structures come in. Could you walk us through what those are and why they matter?
Absolutely. The primary index is what the database uses to organize the main data, often mapping from an ID or key to a record. But in most applications, you want to query by other attributes. For example, by username, email address, product category, or date. That's where secondary indexes come in. A secondary index is like a separate lookup table that maps an attribute to one or more primary IDs or records. To make this work, databases either store a list of matching IDs with each key, like in a full-text search, or they append some unique identifier to the key itself, ensuring everything stays unique. In relational databases, you can use commands to add or remove secondary indexes. They're invaluable for performance. But keep in mind, every time you write new data or update an attribute, any related indexes have to be updated too, which means extra work on writes.
Okay, so adding indexes can make your reads much faster, but your writes a bit slower. It's a classic trade-off, right?
Exactly. That's why databases don't index everything by default. They put the choice in your hands. You add indexes based on how you query the data most often. There are also special cases. Clustered indexes store the entire row's data within the index itself. That means if you query on the indexed column, you can get everything you need from the index alone. In other cases, like covering indexes, you can store selected columns in the index to accelerate particular queries even further.
Now, what about situations where you need to query using multiple columns or dimensions, say latitude and longitude for geospatial data, or a combination of product and date? How do databases handle that?
Great point. For those, we move beyond single-column indexes to multi-column or multi-dimensional ones. The simplest version is a concatenated index, just gluing multiple columns together as a composite key, usually in a particular order. This works well for many real-world queries. Think of a phone book. It sorts by last name first, then first name. But for more complex queries, for example, finding all restaurants within a particular map rectangle, you need spatial or multidimensional indexes, like R-trees. These allow you to search efficiently, not just in one direction, but across several dimensions at once. Some systems use clever tricks, like translating two dimensions into one using mathematical curves, space-filling curves, but for serious geospatial or multi-factor analysis, specialized structures give much better performance.
That makes me think of map apps and ride-hailing services, lots of data points, all needing rapid filtering by geography or even color or category. It's amazing to think about the algorithms making that possible. Speaking of advanced lookups, what about full-text search? How do databases go beyond exact match queries to support things like searching by partial words, synonyms, or even fuzzy matches?
That's a fantastic question. Full-text search is a field all its own, and it's vital for things like search engines and document databases. At the core, full-text search engines build indexes that map each unique word or term to the list of all documents containing it. This is often called a postings list. To handle typos or variations, these systems employ data structures like tries, think branching dictionaries, or finite state machines, which can quickly walk through possibilities and even measure how close a word is to your search using something called edit distance. Open source search tools like Lucene, which powers Elasticsearch and Solr, use SS-table-like storage for these term dictionaries, merging and compacting just as in log-structured systems. They also support features like stemming, handling grammatical forms, synonyms, and wildcards, which brings real flexibility for end users.
That's impressive. So the same underlying ideas, logs, sorted segments, indexes, crop up everywhere, just adapted to the needs of the data. Now, before we shift to analytic databases, I want to touch on something you mentioned earlier, in-memory databases. How does keeping everything in RAM change the storage and retrieval equation?
That's a fun topic. Disks have always been the bottleneck in database performance. They're much slower than main memory, even with SSDs. As RAM has gotten cheaper, we've seen a new wave of in-memory databases. These keep all data, indexes and values, right in memory, offering dramatically faster access. Systems like memcached are used as caches. They can lose data if they restart, which is fine for temporary data. But there are also durable in-memory databases, such as VoltDB or Redis, with persistence turned on. They periodically write change logs or snapshots out to disk to ensure durability, even as day-to-day queries stay blazing fast. Interestingly, the main speed advantage isn't just skipping disks, It's that in-memory databases can use in-memory optimized data structures and don't have to encode and decode data the way disk-based databases do. That removes a lot of overhead.
So, for applications where raw speed is essential, or datasets are manageable in size, or where you care more about throughput than durability, in-memory systems really shine.
Exactly. And there's active research trying to stretch these systems further, letting them spill to disk intelligently when they run out of RAM, or work directly with emerging non-volatile memory hardware.
Awesome. Let's pivot now to analytics. Transactional processing and analytics. The workloads and their requirements are really different, right? What's the divide, and how do storage engines adapt to these two worlds?
Absolutely, the divide is huge. Transactional workloads, often called OLTP, or online transaction processing, are all about lots of small, quick interactions. Updating a user record, looking up a product, writing a comment. Each operation touches a few records at a time and demands speed. Analytics, OLAP, or online analytic processing, is about asking big-picture questions. How many products did we sell last quarter? Or which users spent the most over the last year? These queries often scan over millions or billions of rows, aggregate lots of data, and return insights rather than single records. Storage engines for OLTP treat disk seek time like the main bottleneck. It's all about finding that specific record quickly, often using indexes. In analytics, the bottleneck is different. It's all about how much data can be read sequentially from disk, a problem of throughput and compression. Cut goes here.
Wow, Mike, this has been a comprehensive tour of storage and retrieval in databases. Let me try to recap our main takeaways for listeners. Databases store and retrieve data using storage engines with two main philosophies. Log-structured, like LSM-Trees and SS tables, great for high write throughput, and page-oriented, like B-Trees, common in traditional relational databases. Each has its own indexing strategies for fast lookups, and databases allow you to add secondary or multi-column indexes for more flexible queries. Full text and fuzzy indexes make searching for words, partial matches, or similar values possible. In-memory databases take speed to another level by keeping data in RAM at the expense of durability or dataset size, though new solutions are bridging those gaps. Ultimately, understanding these concepts helps you as a developer choose the right database, design performant applications, and troubleshoot issues when they arise. Mike, thanks so much for joining us and sharing your expertise. Any final thoughts?
Just this. It might seem overwhelming at first, but having a rough sense of how your data is stored and accessed will make you a better developer and architect. You don't need to invent your own storage engine, but picking the right one and tuning it well depends on understanding your application's query patterns and needs.
That's fantastic advice. Thanks again, Mike.
Thanks for having me, Alex.
And thanks to all our listeners for tuning in to the Trending Tech Show. As always, if you enjoyed this episode, subscribe and let us know what tech topics you want us to explore next. Until next time, keep learning and stay curious.